Real-time cooling power attribution for co-located data center rooms with distinct temperatures. Authors of this paper are from Nanyang Technological University of Singapore. Singapore is a digital hub in Southeast Asia. So far, there are a total of 35 co-location data centers on its land of about 700 square kilometers. The data center industry consumes 7% of the country's electricity, and this ratio is increasing due to the business growth. On the other hand, Singapore has set ambitious targets to address climate change. Therefore, to Singapore, it is critical to manage and improve the energy efficiency of the local data center industry. In data centers, cooling consumes about 40% of the energy. Therefore, reducing cooling energy is an important area to work on. From the common sense, if the server rooms can operate at higher temperatures, more cooling energy savings can be achieved. From a general guideline, 1 degree temperature increment can lead to 4% cooling energy saving. So raising the server room temperature set points is a rule of thumb approach to improve the energy efficiency of data centers. To raise the operating temperatures, Ashray has provided the opportunities by extending the allowable temperature range of IT equipment. Specifically, Ashray has defined 4 classes of A1 to A4 for IT equipment to tolerate higher temperatures. Many latest servers are A3 compliant, meaning that they can tolerate an inlet temperature of up to 40 degrees. However, the tenants of colocation data centers may have their own constraints in adopting higher temperature set points. They may run distinct IT equipment with different temperature tolerance. They may have different mentalities in accepting higher room temperatures. Therefore, in our research, we aim at developing mechanisms for a colocation data center to support distinct temperature set points for the rooms owned by different tenants. A key problem is how to incentivize the tenants to raise their temperature set points, subject to their own constraints. The current pricing mechanisms adopted by colocation data centers do not address this problem. Because the temperature set point is not within the consideration of cooling power attribution, in this paper we answer 2 basic questions. First, how to fairly attribute the power of the shared cooling infrastructures to the server rooms adopting different temperatures. Second, there will be heat transfers among the server rooms adopting different temperatures. From our real experiments, the inter-room heat transfer can be up to 9% of the total server load. Therefore, we need to study how to properly address the inter-room heat transfers in the cooling power attribution. Before we present our solution, we briefly review the state of the practice and the related research. The existing attribution policies have 2 categories. The first category performs the attribution based on the number of racks, or the space of the server room. The second category performs the attribution based on the actual load. However, these attribution approaches do not consider distinct room temperatures and inter-room heat transfers. There are existing studies on inter-room heat transfers. Some focus on modeling the heat transfers. There are 2 studies addressing the heat transfers for cost attribution in a multi-apartment building with centralized heating. The in-room heat exchangers in the heating system do not consume energy. Differently, the in-room air handling units in the data center cooling system consume energy. As a result, addressing the heat transfer problem for data centers is more challenging than for the building heating systems. There are a few thesis papers on energy apportionment. They try to associate the residents' positions and activities with the building's real-time power usage. Differently, we aim to attribute the cooling power to server rooms as precisely as possible. So far, I have introduced the motivation of this work. Now I will present the preliminaries and the measurement study. We consider a 2-stage cooling system. The first stage consists of the in-room edge use. The second stage is the shared cooling infrastructure supporting the whole data center. We model the inter-room heat transfer to be a linear function of the difference between the 2 rooms' temperatures. The coefficient alpha depends on the area and the material of the separation between the two rooms. The heat removed by an HU is the sum of the IT load and the total heat from other rooms, which is modeled by a linear function of the mass flow rate and the temperature delta of the water or air going through the HU. The heat removed by the cooling tower is the sum of the power consumption of the chiller plant and the total heat generated by all the server rooms, which is also modeled by a linear function of the mass flow rate and the temperature delta of the water or air going through the cooling tower. We also adopt general power consumption models from an ASHRAE handbook for the cooling devices, including the fans of HU and the cooling tower, water pipes, and the chiller plant. We conduct a set of measurement studies to gain insights. First, we investigate the impact of temperature set point and the IT load on the cooling power. We simulate 10 server rooms with identical IT load and identical temperature set points. The figure shows the relative cooling power saving versus the temperature set point under different IT loads. We can see that the saving increases with the temperature, but it becomes flat. This means that it is worthwhile to increase the temperature set points from the current very low levels. We also see that the power saving increases with the IT load. Second, we investigate the impact of heat transfer on cooling power. We simulate 2 server rooms. The first one has a temperature set point of 21 degrees, and we vary the temperature set point for the second server room from 22 degrees to 31 degrees. The figure shows the breakdown of the cooling power versus the temperature difference between the two rooms. We can see that the second stage cooling power is not affected by the heat transfer. We can formally prove this based on the 2-stage cooling system model. Moreover, the HU consumes more power when there is influx heat from neighbors. This is because the HU fan rotates faster to remove more heat in maintaining the temperature at the set point. Therefore, we need to rectify the HU power readings for charging purpose. Now I will present our proposed cooling power attribution scheme. From the measurement study results, we know that we can address the heat transfer problem and the second stage cooling power attribution problem separately. To address the heat transfer problem, we need to estimate the amount of heat flowed between any two rooms. We consider the problem under a general setting of n server rooms. At a certain time instant, the total heat transfer of a room is the difference between the total heat removed from the room and the IT load. It is also the sum of the heat transfers from with all other rooms. In this equation, those two terms are metered. The room temperatures are also metered, so the heat transfer coefficient is to be estimated. Since we have a total of n rooms, we can write down a system of n such equations, but we have n choose two heat transfer coefficients to be estimated, so the problem is underdetermined. To address this issue, we integrate all historical measurements with temperature fluctuations, such that the number of equations is greater than n choose 2, and the problem becomes determined or overdetermined. Once we obtain the heat transfer coefficients, we can estimate the heat transfer between any two rooms at any time. Now we consider the problem of how to rectify the HU power readings to address the heat transfers. We use a two-room example to illustrate the challenges. Because the power consumption of the HU is nonlinear to the amount of heat removed, the total powers of the two rooms in the presence and the absence of the thermal insulation are different. Specifically, the changes of the two rooms' HU powers due to the heat transfer are different. Therefore, we cannot completely eliminate the effect of the heat transfer. In our proposed approach, we follow a principle of using the HU power change of the lower temperature room as the common rectification amount for the two rooms. This is because we found that the heat transfer normally generates a larger impact on the lower temperature room. If a room has heat transfers with multiple rooms, the HU power change needs to be splitted and attributed back to the other rooms. For how to split, please refer to our paper for details. For the second stage cooling power attribution, we follow the Shapley value principle for a set of fairness properties. However, the computation of the Shapley value is not scalable with respect to the number of rooms. From our measurements, we find that a room's Shapley share largely depends on the total number of rooms n and the room's IT load. For example, the right picture shows a room's Shapley share when n varies and other rooms' IT loads vary in a wide range. This room's Shapley share only has a few percent variations. Based on this key observation, we propose a fast heuristic attribution approach. To compute the share of a room, we assume all other rooms have the same IT load as this considered room. Then we equally split the total second stage cooling power. Lastly, I present the performance evaluation results. First, we evaluate the performance of HU power rectification. We use the case with thermal insulation as the baseline to evaluate the effectiveness of the rectification. The figures show the mean relative errors of the original AHU power readings and the rectified readings. We can see that the rectified AHU power readings are closer to those under the case with thermal insulation, showing the effectiveness of the rectification. Second, we evaluate the performance of the second stage cooling attribution. We compare our fast heuristic attribution approach with the load proportional division approach that is widely adopted in today's colocation data centers. The figure shows the mean relative error of the two approaches with respect to the Shapley attribution. We can see that our approach yields attribution results closer to the Shapley attribution. To summarize, in this paper, we propose a cooling power attribution scheme to support distinct server room temperatures. Specifically, we rectify the HU power to address the inter-room heat transfers and attribute the power of the second stage cooling system to the server rooms. With our scheme implemented, the colocation data center can encourage the tenants to raise temperatures for improved energy efficiency. At the same time, the tenants keen to hotter server rooms will be better incentivized because they can receive cost savings in return. This is the end of the presentation. Thank you.